Hello, good evening everyone. My name is Akhil and I'm currently a PhD student from IIT Madras. So, as usual, we will have this weekly session about questions from week 10. So, you can find these sessions online in the YouTube with the following name: Machinery Fault Diagnosis and Signal Processing, Jan to May 2023 live sessions. So, let's begin the session for today. So, the first question we have is which is the rotating part in an electric motor? A. Armature. B. Field winding. C. Both A and B. D. None of them. Yeah. So the first question is which of the following is a rotating unit in electric motor? Whether armature or field winding, or both are rotating, or none of them are rotating. So the armature is the rotating unit in a electric motor, and field winding is the stationary unit. So it doesn't rotate, it will stay stationary. So this is called a stator, while this is called a rotor in an electric motor. Okay, so armature is the rotating unit, also called as rotor, and field winding is a stationary unit, also called as stator in an electric motor. Now in these electric motors, there will be the air gap between the rotor and stator. So based on that air gaps or the minimum air gap, there are some kind of faults possible. So the changing of the minimum air gap between the rotor and stator will cause faults. True or false? So you have a rotating unit. So in this case, this is the minimum air gap between the rotor and the stator. So if this air gap keeps changing, will that cause faults or not is the question. So if this gap keeps on changing, the electromagnetic field between the rotor and stator changes, so that would actually cause faults in working of the motor. So the changing of the minimum air gap will cause a fault. So there is a specific name for this changing of the minimum air gap. It's called dynamic eccentricity. So as we have seen in our earlier weeks, eccentricity is when it's not aligned or concentric. So when there is a gap between them, then it will lead to some eccentricity. And because the air gap is constantly changing, so this eccentricity is not stationary, so it's changing eccentricity, so it's a dynamic eccentricity. Let's look at the next question. This gap. So this air gap eccentricity, which we have seen earlier, can lead to pulsating radial electromagnetic fields. So the varying electromagnetic fields, which will lead to an increase in the mechanical vibration of the motor. So question is true or false? So it's actually true. So this pulsating electromagnetic fields will actually cause increased vibrations in the motor. Okay. So the air gap eccentricity, which we have seen earlier, will actually lead to pulsating electromagnetic fields, which in turn will lead to more vibration in the motor and then cause premature failures. Let's look at the next question. So when we have this false in electric motor, what kind of vibrations or which kind at which frequencies does the vibration gets generated? Whether at the supply line frequency or twice the supply line frequency or both frequencies. So when you have false in electric motor, gives rise to vibration levels at a frequency of. So the answer is twice the supply frequency. So this is when you are doing vibration analysis for an electric motor. If you are seeing any vibrations at twice the supply line frequency, then you can characterize that there is a error or fault in the motor. So let's say this is the supply line frequency Fs. If without any fault, you should only see a one peak at the supply line frequency. But if you are seeing also some more vibrations at twice the supply line frequency, then that means there is a fault in the motor. Okay. I hope this is clear. Let's look at the next question. So which of the following can cause dynamic eccentricity? Bent rotor shaft, misalignment, mechanical resonance at critical speed. So what is dynamic eccentricity? Dynamic eccentricity, as we have seen earlier, is the changing air gap between rotor and stator, right? So that is the dynamic eccentricity. So when you have bent rotor shaft, let's say the rotor shaft is slightly bent like this. And this is under this is an exaggerated view. Now in this case, this would be the minimum air gap. But as this rotor rotates to a position which is like this, so this is where the minimum air gap will be. So, and it could be different also. So a bent rotor shaft can actually cause dynamic eccentricity. What about misalignment? So if it is connected to a different shaft and both are misaligned, like let's say this, and the next shaft is located here. So this kind of misalignment also could lead to the changing air gaps. So that could also lead to dynamic eccentricity. Then what about mechanical resonance at critical speed? So when you are under resonance, the vibration levels will be more. So it could actually lead to much higher air gaps because of the higher vibrations. So that could also lead to dynamic eccentricity. So all these three will actually lead to dynamic eccentricity. So the answer is all of them. Okay. So the dynamic eccentricity may be caused by bent rotor shaft or misalignment or mechanical resonance at critical speeds. All this can cause the dynamic eccentricity. Okay, let's look at the next question. No. Static eccentricity is not caused by So static eccentricity is that eccentricity where there is a variation in the air gap along the. So this gap is different than this. So there is a very difference in the air gap, but that air gap changes same and at that location only. So then that could be due to ovality of the stator core, because if the stator is not perfectly cylindrical, then that would have some eccentricity, or incorrect position of rotating or starter, because this ovality and this won't change the air gap continuously, so they will only cause static eccentricity. But what about bent rotor shaft? So as we discussed earlier, bent rotor shaft actually causes the air gap to be changing. So that is, it causes dynamic eccentricity. So static eccentricity is not caused by bent rotor shaft because it causes the dynamic eccentricity. But ovality of stator core or incorrect positioning of rotor or stator causes static eccentricity only. Let's move on to the next question. Which among the following is not a vibration based monitoring technique? Machine signature analysis, time domain analysis, motor current signature analysis, none of the above. So the answer here is motor current signature analysis, as you can see in the name, because the electric motors are run by current, and by tracking the current as a function of time and by analyzing that, you can actually characterize the kinds of defects in the motor itself. So if there are any faults in the motor, they actually cause frequency modulations of the signal. So by comparing the current signal of a faulty motor with an ideal motor, you can identify what is the difference or what kind of characteristics does a faulty motor has. So with this, you can actually test with the different kinds of faults and how the current signature varies, and then you can identify those faults later on. And usually the faults in motor cause frequency modulated signals. Yeah. So this mainly works for electric motors because you are actually sending in the current through a power supply, so you can actually track how what is the current, how the motor is taking, how much current the motor is taking as a function of time. So just by analyzing that, you will be able to find the faults in the motors. In time domain analysis, what we have seen earlier, it's usually mainly with the vibrations, and machine signature analysis also mainly vibrations. So motor current signature analysis is where you don't need any accelerometer kind of sensors. You will just track the current that the motor is taking. That's it. Let's look at the next question. The question is thermography true or false type question. The answer is question is thermography based fault identification is best suitable for submersible pumps. So what do you think? So you have a submersible pump, that is a pump, entire pump is submerged in water or some kind of oil bath, and thermography is basically you have an IR camera which can give you or which can show you local temperature spots, any high temperature spots or low temperature spots, those you will be able to identify in the IR camera. So if you have a submersible pump, that is it is surrounded by oil or water on all the sides. Because of that, whatever temperature variations are occurring due to certain faults, the temperature will be dissipated, the heat generated will be dissipated. So submersible results in fast dissipation of the generated heat. So because of this dissipation, you won't see the local temperature rises, so you won't be able to identify the faults. So the answer is false. Then which is the best suitable for submersible pumps? Ideally, in the submersible region, using accelerometers is also not an ideal situation. So you can directly track the current which you are sending to the motor. So motor current signature analysis, MCSA, is actually suitable for submersible pumps. Okay. So this is what is mainly used for the submersible pumps, motor current signature analysis, and not thermography or vibration based accelerometer based testings. Use motor current signature analysis. Let's look at the next question. These are on oil analysis. So based on the type of debris particles in the oil, the type of test which you need to characterize the oil changes. So these following questions will be based on that. So if the size of air debris particles are between 10 microns and 100 microns, then which is the following is a suitable technique? Spectroscopy, ferrography, particle count, none. Spectroscopy is you have a spectrum analyzing either absorption emission spectrum or an emission spectrum equipment with which you can identify the elements or composition of the particles, and ferrography is using magnetic or iron particles. You can identify the materials and the quantities. Or the particle count is you count the number of particles and see how much it is. So which size of air debris particles, when the size of particles are between 10 microns and 100 microns, which is the suitable technique. So if it is between 10 to 100 microns, then ferrography is the most suitable technique. Okay. So if it is between 10 to 100, it's ferrography. Now for 10 to 100 it's ferrography. Now if it is less than 2 microns, then which is the suitable one? Spectroscopy, ferrography, particle count, or none. So when the particles are less than 2 microns, then spectroscopy is the most suitable one. And if it is 10 to 100 microns, then it is ferrography, as we have seen in the last question. And if it is bigger, then it is particle count. The debris particles are greater than 100 microns. Okay, when it is greater than 100 microns, the suitable ones is can just do count of the particles. So the particle count is most suitable. So if it is less than 2 microns, then you go to spectroscopy. If it is 2 to, if it is 10 to 100 microns, then you go for ferrography. If it is greater than 100 microns, then you go for particle count. Okay, so these are mainly for the oil analysis. So when you have oil in this electric motor or rotor systems, this helps take away the heat from the rotor or generated inside the electric components. You can also take away if any faults, if any broken things happens, those debris or the debris due to wear and tear can actually come out. You are taking out the heat transfer and you are also cooling it, and you reduce the friction also as a lubricant. So all these are advantages come because of the presence of oil, and by analyzing that oil you can also characterize what kind of faults that happen or what kind of wear and tear that happen. And for that oil analysis, if the particles are less than 2 microns, you do spectroscopy. For 10 to 100 you use ferrography, and if they are larger than 100 you can do particle count. Okay. Now let's move to the next question. When you have a radiating system or a black body radiator or any kind of radiator, so if there is any temperature, every body radiates if it is above absolute Kelvin, and the energy of this emitted radiation increases with increase in temperature or increases with decrease in temperature, or it doesn't depend on the temperature, or none of this. So if it is more temperature, then it emits more energy. If it is lower in temperature, it doesn't emit that much energy. So energy of an emitted radiation increases with increase in temperature of the body. So because if the temperature is more, that means there is more wear and tear, or there is more heat generation also in this, that you can say from this. How does the increase in temperature of the system influence the wavelength at which the intensity of emitted radiation is maximum? So any body which is radiating heat or radiating energy, as a function of lambda, the energy emitted from that system would be something like this. So this is energy as a function of lambda. So this is the wavelength, that is the energy emitted is maximum. So this is lambda max. This is energy at a given wavelength. Now when you are increasing the temperature, how does this lambda max wavelength increase or decrease? So whether the graph, this energy graph, will move to the right or will it move to the left? So that is the question. So when you are increasing the temperature, the maximum wavelength actually decreases, so it moves to the left. So the lambda max decreases as temperature increases. So this is called Wein's displacement law. Lambda max into T is actually a constant, usually denoted by B. So when you have temperature increasing, then the maximum wavelength decreases. So let's say you have some temperature with the maximum wavelength emission is around infrared. If you increase the temperature of that system, you would slowly the infrared comes to the visible range, and if you increase the temperature much more, then it becomes ultraviolet. Then even higher temperatures will make it X-rays, and even higher temperature will take it to gamma rays. So based on the temperature of the system, the energy at maximum the wavelength at which maximum of the energy is emitted decreases as the temperature increases. Okay, so that's why the gamma rays or the X-rays are much more energetic waves than the visible radiation or the infrared radiation, because they are generated at much higher temperature, they carry much more energy. Okay, so when you have increase in temperature, the maximum wavelength at which that energy is emitted decreases when you increase the temperature. This will happen when you reduce the temperature. Okay, let's move to the next question. Infrared cameras can be used for leakage reduction in pipelines, cracks at building joints, heat generation in electrical components, all of them. So infrared cameras, you basically can detect the variations in the temperature if there are any difference, like let's say some part of the unit is at 25 but some parts are at 50 or lower than that. You can actually detect those variations in temperatures using infrared cameras. Now if there is a leakage in pipelines, So you have a pipeline running and then there are some leakages. So when you have those leakages, there will be a temperature difference because it might be cooler based on the inside temperature of the oil, and if there is air outside and the pipe everywhere will be at, let's say, temperature A. Wherever there is leakage, there will be a slight difference in the temperature, and that you can detect. So you can actually detect the leakages in pipelines. What about cracks at building joints? So those also can be actually detected in a similar fashion. There will be a small difference in the temperatures and heat generation in electrical components. True. If there is any heat generation, then the local temperature will be higher than the surroundings. So you can also detect the generated heat. So infrared cameras can be used for all these: leakage detection in pipelines, cracks at building joints, and heat generation in electrical components. Okay, then we hope this is question is also clear. Now let's move to the next question. Radiography is used to detect internal defects like crack. True or false? So in radiography, you send a set of waves inside an object and you look at the reflections coming from the object. And so when you are sending some waves, if there is a crack inside, they will be reflected here and they again go there and then they will be reflected. So an object without a crack and an object with a crack, there will be difference in the signal from the sensors. So both crack will cause a difference in the received signals. So you can actually detect if any cracks are present. So it's actually true. So radiography can be used to detect the internal defects like crack. Let's look at the next question. The wavelength of the infrared region is 0.2 to 0.4 micrometer. The wavelength of the infrared region. So the wavelength of the infrared is actually from 700 micron or 700 nanometers and above. So 0.7 to 103 microns. This is infrared. So in this also there are multiple regions: near infrared, NIR, and uh, far away infrareds. So infrared is actually from 0.7 to 103 microns, and this is usually visible light, visible range, and this is usually ultraviolet range or blue also. Usually around 365 is ultraviolet, so this is usually ultraviolet and this is visible and this is infrared. So the answer is 0.7 to 103 micrometers. that is the infrared region. Now let's look at the next question. Which of the following is a contact type temperature measurement device? So infrared camera, thermocouple, and pyrometer. So thermocouple is a contact type temperature measurement device. So because of the temperature, it can actually generate an electric signal, and that electric signal or the voltage one can is function depends on the temperature. So thermocouple is the contact type temperature measurement device. In infrared camera, there is no contact with the object, and in the pyrometer also there is no contact. So only thermocouple is the contact type temperature measurement device. Okay, now let's look at the next question. To reduce eddy current losses in electric motor, the stator core is laminated, attached to fins, dipped in oil. So to reduce eddy current losses, the stator motor is actually laminated. So lamination helps to reduce the eddy current losses. Attaching to fins or dipped in oil will actually help in this will help in thermal heat transfer Oil also helps in that, plus oil also carries away debris due to any wear and tear. Okay, so the eddy current losses are actually taken or solved by using a laminated stator core. That is it for this week. I will revise once all the questions and then we can close the session. So, which is the rotating part of an electric motor? Armature, field winding, or both armature and field winding, or none? So, armature or rotating rotor is the rotating unit, and field winding is the stationary unit, also called as stator. In an electric motor, armature is the rotating unit. If the minimum air gap between the rotor and stator keeps changing, then it would actually lead to increased vibrations, so which can cause faults. So the answer is true. The changing of the minimum air gap between the rotor and stator will cause faults. True. And this changing minimum air gap is this error due to that is called the or the fault is called the dynamic eccentricity. Next. Air gap eccentricity leads to pulsating radial electromagnetic fields which lead to an increase in the mechanical vibration of the motor. Yes, if the air gap eccentricity, that is the changing air gap between the rotor and stator, leads to variations in the magnetic electromagnetic fields, they won't be uniform. So this in turn leads to higher vibrations of the motor. So it is true. Faults in electric motor give rise to vibration levels at a frequency of. So when you are using an accelerometer to detect faults in the motor, usually the vibrations will be at twice the supply line frequency. So if you detect any higher vibrations at twice the supply line frequency compared to an ideal motor, then you can see that there are some faults in the electric motor. Dynamic eccentricity may be caused by which of the following? Bent rotor shaft, misalignment, mechanical resonance at critical speeds, all of the above. So dynamic eccentricity can be caused by all the three things which are listed here: bent rotor shaft, or misalignment, or mechanical resonance at critical speeds, because they keep changing the actual minimum air gap between the rotor and stator. All this can change that, so they lead to the dynamic eccentricity. Static eccentricity is not caused by ovality of stator core, incorrect positioning of rotor or stator, bent rotor shaft, none of the above. So in static eccentricity, there is a uneven air gap between rotor and stator in the around this thing. So there is some location where it's minimum air gap and some location where it's maximum air gap, but this stays same. So that happens when the stator core is not perfectly cylindrical, if there is some ovality or elliptical in shape, and if they are not positioned correctly. But when you have a bent rotor shape, this minimum air gap can change as the rotor is rotating. So bent rotor shaft actually causes dynamic eccentricity. So static eccentricity is not caused by the bent rotor shaft. Which among these is not a vibration based monitoring technique? Machine signature analysis, time domain analysis, motor current signature analysis, none of them. In motor current signature analysis, you actually track the current taken up by the motor as a function of time, and you can do the Fourier transform or anything on that current analysis on the current signature, motor current signature. So if there are any faults in the electric motor, they will actually cause frequency modulations to the current, motor current. So you can actually identify the different faults. So because you are tracking the motor current, you are not tracking any vibrations. This is not a vibration based monitoring technique. Thermography based fault identification is best suitable for submersible pumps. When you have a submersible pump, the oil surrounding or the water surrounding takes away all the heat generated in the pump or the motor. So if you do a thermography using infrared camera, you won't be able to actually detect the temperature changes that easily. So it's not actually suitable for a submersible pump. So answer is false. But because you have a submersible pump and electric thing, if you use motor current signature analysis, that is actually better suitable than using accelerometers also. So for submersible pumps, motor current signature analysis is best suitable. Which size of where debris particles are 10 to 100 microns, which of the following is a suitable technique? If the sizes are between 10 to 100 microns, then ferrography. So these are when you can analyze the oil inside a electric motor or a transformer system which has oil, and if there are any wear and tear between these things, there are the debris forms, and you can analyze this debris by collecting the oil which carries the debris. So if the size of the particles are less than 2 microns, then spectroscopy is the most suitable technique. If they are between 10 to 100 microns, then ferrography, and if they are larger than 100 microns, then particle count is the suitable technique for analyzing the oil. Okay. So any body which is temperature higher than absolute zero radiates some heat, and the temperature of the system decides the energies, and if it is in the higher temperature, it will actually generate much more energy. So the energy of emitted radiation actually increases with the increase in temperature. How does the increase in temperature of the system influence the wavelength at which the intensity of emitted radiation is maximum? So when the temperature of the system increases, the maximum wavelength at which the energy is emitted actually decreases. because X-rays are more energetic than visible, which are more energetic than infrared. So more and more temperature, the wavelength shifts towards the visible and ultraviolet. It's called blue shifting. So the actual maximum wavelength decreases if the temperature increases. But if the temperature is decreasing, then it's called red shifting, where the wavelength increases. So the lambda max is inversely proportional to the temperature of the system. Infrared cameras can be used for leakage detection in pipelines, cracks at building joints, heat generation, electric components. All of this will cause local temperature differences than the surroundings. So you can actually detect them using an infrared cameras. Radiography is used to detect internal defects like crack. True, radiography you can send signals inside an object and can detect the signals using a sensor on the other side or on the same side as the transducer or the signal generator. Now if there is a crack inside it, the signals which you are receiving on the receiver end will be different than a system where there are no cracks. So you can actually detect internal defects like cracks using radiography. The wavelength of the infrared region is around 700 to 10 or zero point 0.7 micron to 103 micrometers is the infrared region. Below zero point 0.7 from till zero point 0.4 is visible, and below that is ultraviolet, and even below that you will have X-rays, and below even that you will have gamma rays, and above infrared you will have microwaves and radio waves. So the wavelength of the infrared is actually in between 0.7 to 103 microns. Which is contact type temperature measurement device? Thermocouple works on the contact based, is in contact with the temperature, high temperature device. It actually absorbs the temperature and can generate voltage, which you can, voltage is proportional to the temperature, so you can measure the temperature. So it's a contact type temperature measurement device, whereas an infrared camera and pyrometer are non-contact based temperature measurement devices. To reduce the eddy current losses in an electric motor, the stator core is laminated. So the lamination of the stator core reduces the eddy current losses in an electric motor, and attaching to the fins or dipping in oil actually helps in other functions like it reduces local heat buildups or the temperature buildups by transferring the heat uniformly, and it can also carry away any debris which are happening because of the wear and tear of the rotor or stator. So they don't work for reducing the eddy current losses. The lamination helps in that. Yeah. So yeah, that is it for today's session. We'll meet again next week. Thank you.